you can think of voids as preserved pockets for our universe. And knowing more about dark energy will tell us what is the destiny of our universe.
So, what is a cosmic void?
As the name says, one will tend to think that cosmic voids are empty. Cosmic voids are not really empty. It's like less crowded areas of our universe, if you see what I mean. And what is absolutely amazing is that these are, in fact, the largest regions of our universe. And it's only with the last few decades where we can actually build huge maps of the galaxy distribution. And in these maps, we can find those regions with fewer galaxies that are known as cosmic voids.
Can you kind of put it in a perspective that somebody like me would understand? Like, okay,
Mhm.
it's an empty space. Like, I get it, but in my mind, I can't kind of quantify how empty the universe or full the universe would be.
Voids are of sizes of tens to hundreds of megaparsec. And because this doesn't really, speak to us, I'll try to give a bit of an idea. We know that light takes time to reach us. For example, the light from the sun was emitted 8 minutes ago and is just reaching us now. So it takes 8 minutes to go all the way from the sun up to us. And if we were to, think of the time that it will take for light to cross voids, it will basically be of the order of 300 million light years. So, it's really huge distances. And over those distances, we may have, maybe 100 galaxies or something like this. So those are extremely isolated galaxies that live in very quiet spaces of our universe.
Do we know how they would have formed? Like, why would these parts of the galaxy, or the universe rather, be empty and other parts would be crowded?
If we think of the primordial universe, there were already tiny regions where there was a little bit less matter, and those regions became emptier and larger, so forming the basis of the structure that we see nowadays. So we call this the large scale structure of our universe. So looking at the distribution of galaxies, we see that it's not, a uniform distribution in some sense. There are regions where we have a lot of galaxies and regions where we have fewer galaxies. So the regions where we have lots of galaxies are called clusters of galaxies, and then the emptier regions where we have very few galaxies are called cosmic voids. And it makes this beautiful pattern.
But why would it cluster in one area and be empty in another? Like, why wouldn't this all ultimately kind of homogenize over time?
So basically, there are two different effects that are going on. On the one side, our universe is expanding, and on the other side, so it's becoming, larger and larger. And on the other side, we have gravity. So gravity likes to pull things together. So the combination of these two effects actually makes what our universe is seen today. So imagine, for example, that you have a galaxy that is sitting on a very crowded region of galaxies. It's very hard for this galaxy to move away because it's attracted gravitationally by the other galaxies. On the other hand, a galaxy that is all alone inside a void is in some way more free to be attracted towards the local cluster. So you can imagine as, matter wanting to grow those perturbations, those variations in density. And so emptier regions will become emptier and denser regions will become denser.
What can we learn from the voids that we couldn't learn from studying the clusters?
This is an awesome question. Thanks a lot for asking it. So basically, the idea is that we know that our universe is expanding, and this is already super surprising. But what is even more exciting is that a few decades ago, observations started to indicate that the acceleration, the expansion of our universe was accelerating. So not only our universe is becoming larger, and that's already, interesting and surprising, but this is happening faster and faster. So our universe is becoming larger and larger, and this is happening at an accelerated rate. And we don't know why. So because we don't know why, we basically believe there may be a component that is called dark energy, which, we really don't understand. And so we say, okay, maybe this component, this dark energy, can be responsible for the acceleration of the expansion of our universe. So taking, you know, the galaxies in the universe, because the universe is expanding, they're being pulled away one from the other. So the universe is becoming larger and larger. And responsible for this will be dark energy. Now, why are voids interesting in this respect? Because by definition, voids are regions where we have very little matter. And if there is one thing that we believe dark energy is that it's not matter. So, in some sense, voids are dominated by this component. We know that voids are going to be dominated by dark energy. So, if we want to understand why our universe is accelerating its expansion, we need to look into those regions where there is very little matter so that the signal from dark energy can be captured nicely. So those are the regions where we expect to have answers about the most crucial, questions in cosmology nowadays.
If we were to kind of look at it as, okay, on a scale of 1 to 10, 1, we know absolutely nothing about these voids. 10, we got everything figured out. Where do you think that we would be on that scale?
I think it really depends on the application. And if you allow me, I'll give a bit, some details on this. Basically, with voids, there are very different things that we can do. Once you have, you take a map of the galaxy distribution and you find regions with fewer galaxies. So you say, okay, these are my voids. These are my pockets that I'm going to call voids. I can do different things with those. I can look at their shape. I can count them. And so all these different applications, they will tell us different things about our universe. And they're not at the same level. So to answer your question, where are we right now in terms of understanding voids? It depends. For example, we have a pretty good model that predicts how many voids we should have in our universe. Another thing that we understand well is what is the shape of voids, not on a one by one basis, but on average. So if you look at voids, even though our universe on very large scales doesn't have any preferential direction or position, voids, as a matter of fact, they will have locally very weird shapes. Some will be elongated, some will be more roundish, some will be, completely distorted. So it's very hard to predict their shape. But what we can do is to look at such voids and look at, on average, what their shape should be.
The thing that I've never understood about, okay, so the universe is expanding, but like, what is it expanding into?
Well, I guess that's where you can put some limits to science because in science, we often need to be able to prove things and test things. And as of now, when you think about it, what we can test is what we see, and we are inside our universe. So what we see is that our universe is expanding and we can measure, the distance between galaxies and we see that that distance is increasing. But that is so far all that science can say. We cannot go farther
Yeah.
than that.
Are we in one of these voids?
It's harder to measure things locally. And so we actually see that our galaxy is part of, a local group and this local group is going to move to the local cluster. And so in the end, the universe is emptying and emptying.
So we're kind of moving into a cluster.
Yes. And this is generically true for most galaxies, right? Generically, if you're galaxies are first going to move towards filaments. And then those filaments are going to, like roads, bring matter into the clusters of galaxies.
So if we were inside one of these voids, like in the middle of it, what would space look like to us?
So, in some sense, locally, you wouldn't perceive any difference at all. The only way to actually measure the movements of galaxies on very large scales is by looking at, these very large surveys that actually measure the light from galaxies far away and see how they move in the sky. So it is not, because the scales are so large, it is not something that we can perceive.
Does space behave differently in these areas?
The question really depends on whether you ask it locally for us or on a very large scale. So from a human perspective, my answer is no, because as a matter of fact, whether I'm on a galaxy that is sitting on a void or on a galaxy that is inside a cluster, for me, I mean, I'm on a planet, I'm going to feel the planet's gravity and that's it, right? So it's not going to make any difference for me as a person. However, on cosmological scales, things might be very different. For example, galaxies that live inside voids, they will, for example, interact less with other galaxies because they never meet other galaxies in those, under dense regions. And so there are fewer things such as mergers of galaxies and all these complicated effects that astrophysicists try to model. So in some way, you can think of voids as preserved pockets for our universe, regions where very little happened on cosmological scales. And this is precisely the reason why they are easy to model because we don't have a lot of complicated effects. We don't have nonlinearities. We don't have things that will, make our theory more complicated.
Are you ready for some harder slash listener submitted questions?
We'll see.
Are voids the exception or the rule?
I would say they are the exception in terms of the amount of information that we can get. Because they provide, as I was saying, very clean information. They're also a region that was not, seen and studied until very recently. So they are new and they provide a link to things that we want to understand the most nowadays in cosmology. However, when you look at our universe, they're not the exception at all. The universe is filled by voids. Basically, voids are ruling the universe in the sense that most of the volume is occupied by voids.
It's occupied by voids in the sense that, like, no, it's the void itself, or like it's a void in that most of the galaxy is empty space. I don't know in my mind, somehow that question is different. I don't know if I phrased it right, but somehow it's different in my mind.
The idea is that most of the volume of the universe is occupied by regions with very few galaxies. So, of course, not completely empty, but where we have fewer galaxies. And while, of course, clusters occupy tinier regions of our universe.
What would finding out more about dark energy ultimately teach us? Like, okay, if we find out that it's dark energy, is this the kind of thing like, okay, we found it, or does the fundamental knowledge change with that?
Knowing more about dark energy will tell us what is the destiny of our universe. Because we know that dark energy is driving this accelerated expansion of the universe. So it's making our universe becoming larger and larger, and this is happening faster and faster. So understanding dark energy means that we can understand how our universe will change.
Yeah, that's one of those things right after you said it, like I really thought about that. I was like, oh, that seems really important. Which one is the biggest one? Is there one that kind of seems to dominate over the others, though?
So there are interesting voids that we can look at, and for example, a famous one is the Boots voids. But I will say that because I'm looking at extremely large scales, um, I really like how at first we were only able to see a tiny slice of our universe and only have a hint of the existence of those voids, and now we see something like 6,000 voids. So I can finally do all my studies with, statistics.
What? How come we weren't able to discover them sooner?
Because in order to observe voids, because they're so big and, and also they have very few galaxies, you need to have surveys that cover large volumes of the sky. And so just to give you an idea, DESI right now, the Dark Energy Spectroscopic Instrument, is mapping roughly 1/3 of the sky, which is big enough for us to see those regions. But not only you need to be able to map those regions, you also need to be able to measure and observe the faint galaxies because those are the ones that are going to be populating voids. So if you're only sensitive to the most luminous ones, then it's harder to actually see the whole this cosmic web of structures that we see. So voids are one of the few tools that need both volume. So we need telescopes that observe very wide areas of the sky and also a very high sensitivity to low mass galaxies. And this is something that only recent technology can give us.
Were people really surprised when they found this, or was this something that, okay, we know this is going to be there, we just haven't found it, or was this like, wait a minute, what the hell is this?
People were absolutely surprised. There was a very important paper in 1986 from Valérie Delaparent and Margaret Geller and John Ukra, which for the first time showed a slice of our universe where you could actually see that the matter and the galaxies were distributed in this non-random way, was following voids and filaments and clusters. And even though people were trying to model these things, they were at first absolutely surprised to see that this was how the universe looked like at large scales.
Is there, when you look at it overall, the universe, is there like a pattern to where the voids are? Like, okay, you got a supercluster, we're going to have a void. Or are they just kind of like somebody just all over the place?
I will say there is no, even though there is some kind of pattern, there is no regular pattern or some kind of fractal. These things is not something that we see in observations.
They're just kind of all over the place. Like you never can tell where one's going to be.
Yeah, exactly. So basically, you can statistically, study the distribution of voids or actually also distribution of galaxies. For example, to what is called the two-point correlation function that gives you the probability if I find a void here, what is the probability that I'm finding a galaxy here for the void galaxy cross correlation function. But other than, statistically, it's very hard.
I feel like this question is going to make no sense. So bear with me a little bit, right? But if we go from the Big Bang, which everything was kind of condensed into one area, and then it expanded, and the voids formed as the universe expanded, are the galaxies in those voids made of something different? Like, why would that area not have stuff in it? Like, is there something different about the mass or whatever that wouldn't have kept things close to it? Does that make any sense?
So generically, it's a very today question because nowadays, because we finally have access to voids, we're trying to understand whether the properties of galaxies inside underdense regions are very different from the properties of galaxies in overdense regions. So it's more the other way around, right? We are finally accessing those voids. We can look at those galaxies with very deep surveys, and then we're trying to understand whether they're different or not. One thing that seems, consensus is that galaxies in voids have a somewhat lower mass. But all these studies are, just starting because void cosmology and even the study of galaxy evolution for void galaxies is something that it's relatively recent, I would say, in the field.
Okay. Even though you basically said, like, we're still figuring out, I'm going to ask the question that probably doesn't have the answer. But why would they have less mass? Like,
Well, in some sense, for example, you can think if I'm a galaxy and I'm sitting in a region where I'm not finding other galaxies, things like mergers of galaxies, which is when you have pure galaxies that become one galaxy, are going to become more rare. So this is the one example of things that could have an impact. Generically, in regions that are known as voids, there is also less matter. And as a matter of fact, matter, and more precisely dark matter, is the seed for galaxies. So if you have less matter, it's also less likely that you have, extremely massive galaxies.
there was something, and then it just kind of snowballed over billions and billions of years. Like, there was something different about them, and then they just didn't evolve the same way that other places did.
Yeah, it's because they were in underdense regions. So the initial perturbation of our universe indicated regions where we had a little bit more matter and a little bit less matter. And this tiny difference that we already see in the primordial universe leads to the formation of structures that we see nowadays.
Let me follow that up with this brilliant question from our audience. Could voids explain why we haven't found aliens?
I think what really explains why we haven't found aliens, it's mostly because the universe is so big. And, we are very, very far away, and we're very, very tiny in this huge universe. So definitely, I don't think that voids are the reason why we haven't found aliens.
Do you ever find yourself thinking like, oh, this can't be real? Like, the universe can't be that big. There can't be all this. Because to me, like in my little house in Seattle, like, no. No.
So
Like,
very
really?
often, very often, what I like to do is to, and I do this with my children too. So I like to think about scales, right? And it makes me think there was this beautiful book that was, popular a few years ago. It's called Powers of 10. And, it starts from a hand and then it goes away, the universe increasing in powers of tens. And then it also goes inside the human body. And I think that the fact that scales are all around us and mathematics is the language that we need to speak to really understand that those scales is something that helps me a lot. And in really feeling how real all of this is, how real science is.
Like, what do you think is the single most interesting about thing about
So
voids?
I think the whole community in cosmology right now really wants to understand dark energy. And when you don't understand something, one of the first things you're going to do is to look whether it changes or not with time, right? And because voids are ruled by dark energy, they're dominated by dark energy. I think voids are in a pretty good position to tell us if dark energy changes or not with time. And so I'm hoping that if we go ahead with upcoming data, we can actually make a measurement from voids on the properties of dark energy, which will really wow a lot of people in the cosmology community and outside of it.
Do you think the solution will be more complicated or less complicated than we think that it's going to be?
Um, I don't know. I think it's good not to know the answer for now.
Um, but so we have the voids. So then there obviously would be the opposite of that, where we would have just, are there places in the universe that are just massively, massively packed together?
Yes, clusters. So, and you will say, why can't we use clusters to extract cosmological information? Well, we can, but because gravity is what is really pulling those, regions together, these clusters of galaxies, as a matter of fact, it's very hard to extract information and learn something about dark energy because gravity is ruling there. And whenever gravity is ruling, things become very highly nonlinear. And this is so complicated to model. One of the good things about voids is that they are simple. They behave linearly. We can model them. They just mostly expand. And so this means that mathematically, the models that we use can go straight to the point and measure things in an easy way.
Are there any voids that are shrinking?
So the theory tells us that there should be very, very tiny voids. Imagine basically you have an underdense region, and around it you have, galaxies. Those galaxies will want to be attracted one from the other, and so they may eat the small underdensity away. So those are local, tiny underdensities sitting in high density areas. So yes, some tiny voids may disappear out of existence. Our theoretical model predicts this, but currently we are not able to see those scales with modern telescopes.
But is there any place that we know of, like, oh, there is just nothing there? Like, this is not just a void, this is like a super void in the sense that, like, not only is there very few things, there is nothing there.
So there are absolutely very large regions of space where there are no galaxies, and can go on from megaparsec and megaparsec, and there are no galaxies. But if you move in the universe, so basically we know that there are, superclusters and supervoids. So regions where really galaxies are an extreme rarity. So the short answer is yes, those regions exist.